Okay, this is a recording of 1-2B worksheet solutions. Don't worry about this date. I put the date in there last year. Starting out with, we're going to talk about these piecewise defined functions is the first thing that you have to graph. I typed this up like this and put this here for you. A lot of times I'll put the T-chart already in there on tests and quizzes. Here you did have to draw in your own T-chart on this particular version. Okay, so notice I need to look at two different parts of this graph. Each line is a different piece. That's where piecewise function comes from. Each piece is going to be determined by a functional portion and by a domain. So in other words, when x is less than 0, the output from the function is always 1. So whether I plug in -1, I get out 1, -2, I get out 1, -3, I get out 1. That's a horizontal line. Notice we have an open circle here. The biggest problem when students graph piecewise functions is they don't put the open circle where it needs to be. So I'm not supposed to plug 0 into this first piece, into this top piece. But if I were to evaluate the top piece at 0, I would get out 1. And the only difference is I put an open circle there instead of a closed circle. That's it. Because I do have to evaluate 0 in this bottom piece, which is the square root of x. And the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. We plot those points and we graph it. I'm going to use a little bit of terminology when I'm going over this that you're going to hear again and again and again in chapter 2. This is a function that is not continuous, okay? Because it has what is called a discontinuity at x equals 0. What does a discontinuity mean? Well, there's a couple different types of discontinuity, and this type is called a jump discontinuity because we're going along with this horizontal line and then it stops and it jumps down to start this other function. It's called a jump discontinuity. Other times we'll graph piecewise functions that are continuous. So on problem 34, notice I can only plug in values that are less than 0. Now, I'm not supposed to plug 0 in, but I need to. If I plug 0 into this top piece, I'm starting right here at 0, 0. It's just an open circle right now. Now, this piece may fill in that circle, but the key is to know where the open circle is. It's an open circle for now while I'm graphing this parabola that opens upward. We have to recognize x squared is a parabola. As a matter of fact, if I take -1 and square it, I get 1. -2 and square it, I get 4. -3 and square it, I get 9. That is this left-hand side of a parabola opening upward with the vertex at the origin. It's just right now, this vertex would actually be an open circle if I only graph that first piece. Many times, the next piece will fill in any open circle that you may have from the first piece. When I plug 0 in, 0 cubed is also 0. So that fills in that piece. You never want to have a dot and then a circle around it. It's either filled or it's open. It's one of the two. Don't have a dot with a circle around it, then I can't tell if it's supposed to be filled or open. I'm supposed to plug 1 in here. 1 cubed is 1. But then that's it. So really, this is a cubic function. It flattens out here a little bit. It's a little bit more flat than what the parabola would have been. Okay? So I could plug a half in and I get an eighth out, for instance, if you want to consider that value. Okay? And then from this point on, again, I'm not supposed to plug 1 into here. And this is where it's often forgotten. I still have to plug 1 into here because I may start with an open circle that's jumped up or down. But when I plug 1 into this piece, I also get 1 out. So I'm starting right from this closed circle here at 1, 1. I don't have a jump discontinuity. Where this piece left off, the third piece, this linear piece, takes off right where this left off. That's why it's continuous. Now, if I plug other numbers in, like 2 and 3, I plotted a couple of those. It's just a line with the slope of up 2 over 1, up 2 over 1. But This is called a continuous function because it is a nice continuous transition from the parabola that opens upward, the cubic function opening upward, turning open upward, and the linear function that continues from where the cubic left off. Continuous, not continuous. Okay? I mean, it makes sense when you see that. Okay, then we get into some easy ones here. What is a function? What is not a function? This does not pass the vertical line test. I drew one in, not a function. This does pass the vertical line test. This is not a one-to-one function because if I draw a horizontal line, it'll cut it in more than one spot, but it's still a function. It passes the vertical line test. Every x only corresponds to one y. This is a function. Even though we have these jump discontinuities, that's what these are called, jump discontinuities. The graph is jumping, right? If I'm going this direction, it stops, open circle, it jumps down before this starts. But even if I draw a vertical line through this point, it has a solid dot here, but it's open there. So every x is only defined in one spot. This is that greatest integer function. In your calculator, it's int function. It's under your math over to number. I believe it's number 5 in your graphing calculator. Let me just show it to you quickly so you can see it. So if you go math and over to number, this int will give you that. Some of you know it as the step function. Now, when I say you've seen this last year, some of you maybe did, maybe you didn't. Okay, but you're going to see a function that is many functions that are like this, that have these discontinuities are called step functions. But this is a function. Every x only has one y. This is not a function. I drew a vertical line in right there for you, so you can see that this is not a function. Now, on problems 41 through 46, we're actually taking the picture and writing the piecewise functions. A couple things I'm going to try to stress early on, but I won't on every problem that I'm going to discuss. And what that is the fact you have to write these using correct notation. It's always f of x equals or g of x equals, whatever you want to call the function. But you have a one-sided brace. Don't close the brace. It's a one-sided brace. And your functions need to be from left to right is presented top to bottom, so that the domains are always defined from left to right. Meaning this first line segment right here between 0 and 1, it's a line, so it has a slope of up 1 over 1, m is 1, and a y-intercept of 0. So there it is. It's just x. It's y equals x. But it's only defined to be y equals x between 0 and 1. Notice I have an equal to at 0 because it's a closed dot. I have an equal to at 1 because that is also closed. Now, you could define 1 either in this piece or this piece. It doesn't matter, but not both. Otherwise, it's not a function. It can only be defined once. The second piece has a slope of down 1 over 1. It has a slope of negative 1 times x. And if I go up 1, back 1, I'll be up at 2. You could do that, or you could do point slope. Start with a slope of negative 1, going through this point, and figure it out using your point slope formula. But it's easy enough just to count to see where that y-intercept is going to end up. That defines this piece. But this piece is only defined between x equals 1 and x equals 2. There it is. But it's always the function, comma, then the domain. Function, comma, then the domain. The functions should be presented top to bottom, should be presented left to right. Okay? Notice here, since I defined this piece at 1, I don't want to do the same thing here. But the equal to could have been here or here in this case. It's a nice continuous function. And again, x is less than or equal to 2 because we have that solid dot. So x are values between 1 and negative 2, but not including 1. Yep. Don't use interval notation on this. We almost always exclusively, we want to use inequality notation when we're presenting domain for piecewise functions. Look what happens here. This sometimes is confusing. The ones that you've had to write on AP tests recently, and there's not a lot of these that you have to write necessarily, but they tend to be just kind of the nice horizontal variety. And we're going to see these again when we talk about velocity and acceleration. Here's the key. This is just a horizontal line. The output is always 2. When is the output 2? Well, it's 2 between x is 0 and x is 1. Notice no equal to here because it's got that open circle right here. I can also, if it's the same function in 2 different spots, I don't have to list it twice. It's okay if you do. I can just say comma and list the other piece that has that same output. So it's also 2 from x equals 2 to x equals 3. Notice included here, not included here because of that open circle. So what's happening between 1 and 2 and 3 and 4? Well, look, I have a horizontal piece again, but the y value is always 0. And x is greater than or equal to 1 because of the solid dot, less than 2, open. And from x is greater than or equal to 3, solid dot, x is less than or equal to 4 because of the solid dot. So all of these equal to signs are extremely important. This is the only way that this should be presented. It should not be presented in reverse. The domain should not be presented first. The function, then the domain. Let's take a look at this one. This is a more interesting situation. We have 2 line pieces. This line here is down 1 or down 2 over 2. Negative 2 over 2 is negative 1. That's the slope, negative 1. It's going downhill, so the slope is negative. The y-intercept is 2. We can see from the graph. Even though it's not a solid dot, this line would go through 2 if it was the entire line. This is what's going to restrict what portion of the line it is. We're only defining the output values in this way when x is greater than 0 and less than or equal to 2. So between 0 and 2. But notice that 0 is an open circle. That's why no equal to. Where at 2, there's a closed. It's a closed dot. Therefore, it's included when x equals 2. This piece here is a little bit harder to determine. The slope, they're telling you this point is 2, 1. So I'm going down 1. I'm going over 3. 1 over 3, but the slope is negative because this is going downhill from left to right. How do I find this y-intercept? Well, it goes through this point. Use the point slope form. I showed how I actually calculated the slope by subtracting y's over subtracting the x's, but you could count. I say it goes through this point, so I use my point slope formula. Y coordinate plus the slope times x minus the x coordinate. We did this extensively in section 1. Distribute, and that's the equation of my line. Now, it never gets back to 5/3, but that's okay. We restrict the domain here. We say this line is defined to be negative 1/3 x plus 5/3. However, we're only defining the line from the x values of 2 and 5. Notice 2 does not have an equal to because it has an open circle on the left end of this segment. 5 has a closed circle. Therefore, we have the equal to. Here's another one that's made up of 2 lines, very similar to the one we just looked at. From left to right, start at the leftmost portion. This has a slope of down 3 over 1, negative 3. And it also goes through the y-intercept of negative 3. So it's negative 3x minus 3. This is only defined from x being negative 1 to x being 0. It changes after x becomes 0, it changes to this line. Notice solid dot here means equal to on the 0. Open dot here means just less than, no equal to under it. That's the first piece. Working from left to right, we've defined this piece. Now we've got to define this second piece. This slope is down 1, 2, 3, 4 over 2. 4 over 2. Notice it's negative because that's down. This is positive because it's to the right, is -2, or you can just count. Just make sure you know slopes that go downhill from left to right are negative. And the y-intercept we can see is 3. We don't have to do extra work if we can tell that y-intercept would have been 3 had this line continued. So there is the line. But this line is only defined between 0 and 2. X has to be greater than 0, open circle, less than or equal to 2. 45. 3 pieces, a negative slope, a horizontal line, a slant line with a negative slope. So here we go. On this first one, the slope is -1, down 1 to the right 1. This is only defined between -1 and 0. X is greater than or equal to -1 because of the solid dot. X is less than 0 because of the open dot. That defines the values between -1 and 0, inclusive at x equals -1, non-inclusive at 0. This is a horizontal line of 1, so it's just 1. Again, open dot, so not inclusive at 0, inclusive at 1. You could have had the equal to either here or here in this problem. Either way would be fine. It should not be in both, though. So this is an error. There should not be an equal to in both of those. This should be eliminated here or here. Doesn't matter. That's a mistake on my part. I told you there will be some mistakes, and I'm going to point those out as we go. Okay? That other piece then has a slope. The slope of that piece is down 1 over 2. It's easy enough just to count it. Down 1 to the right 2. Or you can subtract the y's over subtract the x's. How do we find the y-intercept of this? This gives students difficulty sometimes. Just remember, if you have a slope and you know a point that the line goes through, any point that the line goes through, use the point slope formula. Y equals 0, so we don't have to write that down, plus the slope, -1/2, times x minus the x coordinate, just like we did in section 1. Distribute, because we want to present these lines in slope-intercept form when we're writing these piecewise functions. Again, it's defined between 1 and 3, closed circle at 1, open circle at 3. That's why I put the equal to there too initially, but I shouldn't have it because I already defined it up here. Okay? No, definitely no equal to on the 3. 46. 3 pieces. Slant line with a positive slope, slant line with a negative slope, and a horizontal line. This slope is up 1 over 2. It has a y-intercept of 0. There's the slope. We don't need to put plus 0 because the y-intercept 0. It's defined between -2 and 0. Both have solid dots, so we have inclusive on both. This slope is down 2 over 1, so the slope is -2x. The y-intercept is clearly 0, or is clearly 2. This is defined between 0 and 1. It's open when x is 0. That's why we don't have an equal to here. It's closed at x equals 1. That's why I have a closed here. Notice that all of these piecewise functions, they don't put a closed twice. They never will, because it won't be a function. It's no longer a function if that is the case. It cannot be, a function cannot have 2 y values for one corresponding x value, okay? Or for any x value, you cannot have 2 corresponding y values. So it's between 1 and 3. Pretty straightforward, nice, easy problem. I don't think there's anything too difficult about that one once you get them down. That leaves us with the true false. Oh, no, we do have one more. We have problem number 50 here. A couple more. For problem number 50, the key to this is it says, write the absolute value function as a piecewise defined function. Then draw a complete graph of the function, state the domain and range in both set builder notation as well as interval notation. Here is how you break these up. There's often questions about how do you know where the break occurs? The break occurs wherever the argument of the absolute value piece equals 0. This argument equals 0 when x is -4. So I have to look at x to the left of -4 different than when x is greater than -4. So here's why. If I plug a number in that's less than -4, if I plug in -5, I get a negative number in here. How do I make a negative become positive? I negate it. So when you first learn absolute value, you probably learned if it's a positive number, leave it positive. If it's a negative number, make it positive. What does make it positive mean? Is it magic? Poof, it becomes positive? No, mathematics is not magic. It's magical, but it's not magic. How do we make a negative become positive? We negate it. If I negate a negative, it becomes positive. So any number that is less than -4 will produce a negative number inside these bars. So I have to negate what's inside the bars when x is less than -4. That's why I have negated each term inside the absolute value bars to eliminate the absolute value bars. I distribute the 2, collect like terms. -8 minus 3 is -11. Where if x is greater than or equal to -4, and again, the equal to could be here or here. It really doesn't matter. But if I pick a number like -3, I get a positive number. -2, I don't have to do anything. I can just eliminate the bars. I do not have to do anything with the argument because I'm already going to get a positive out every time the number is greater than or equal to -4. Now I distribute. 8 minus 3 is 5. This is the left-hand piece. This is the right-hand piece. That's why you always want to work from left to right. This piece should be first, comma, when x is less than -4. This piece is second when x is greater than or equal to -4. The domain for most absolute value situations, not all, is all real numbers. We can plug anything in. Here's how you write it in interval notation. The range, we got to graph it. Again, most interesting value of x is -4. If you plug -4 in, +4 is 0, times 2 is 0. 0 minus 3 is -3. And now, really, if I want to, I can just count out the slope. I know it's going to go up 2, back 2, up 2, back 2, up 2, back 2 to get this. Then it's going to stop being that negative slope. And this function says, I want to turn to the positive side. I'm going to become positive. And now from that same point, it's going to go up 2 over 1, up 2 over 1, up 2 over 1. And here's that V shape that you're used to from graphing absolute value. You can get a graph of this by just point plotting. I understand that. I want you to point plot it. But I want you to understand how these two pieces define the same picture. Because any calculus that we perform on an absolute value situation, we have to write it in piecewise format first in order to do some calculus interpretation. In other words, there is no derivative rule for absolute value. The absolute value must be broken into a piecewise function to apply derivative rules in calculus. So keep that in mind. All right, composites. F of g of x. These you should have covered extensively in Algebra 2 and pre-calculus. So on this particular problem, I'm taking x, I'm plugging it into the g function. What comes out when x goes into the g function? X minus 1 comes out. So that's the new input into the f function. Whatever the output of g is becomes the input of f. So x minus 1 is coming in to the f function. Well, the f function says whatever comes in, add 1 to it. X minus 1 plus 1 is x. That's nice. Let's do g of f of x. Take x, plug it into the f function. This time, x plus 1 comes out. That is my output. This is my output from f of x. But now that output is the new input into the g machine. The g machine says, whatever comes in, subtract 1 from it. Well, this is what's coming in. This is the input now. When I subtract 1 from it, the 1's cancel, and I get x. Remember what happened is if f of g of x equals g of f of x equals x, if they both equal x in either order, that means these are inverse functions. Okay. Or we're going to find that out actually in the next lesson, I should say. When you plug 0 into G, if you plug 0 into G, you get out -1. And if you plug -1 into F, -1 plus 1, you get out 0. You can also get this now that we've done this composite. You can get it by just plugging it into the composite. Yeah, if 0 comes in, 0 comes out. Same here. If 0 comes in to this composite, 0 comes out. But now look what happens here. G of 2. Plug 2 into the G function. Here it is. 2 minus 1 is 1. 1 is the output. That's why we now have to evaluate G at 1. This 1 right here is the output from G of 2. Now I plug 1 back into the G function. If I plug 1 into the G function, 1 minus 1 is 0. Therefore, this composite equals 0. What about here? F of x. Take x, plug it into the f function. Well, this comes out. If x comes in, x plus 1 comes out. That output is now the input into the f function. F of x, the output is this. X plus 1 is now the new input into f. The f function says, is defined, anything that comes in, add 1 to it. X plus 1 comes in, add 1 to it. X plus 2 comes out. That's a composite. Notice I wrote down here, since f of g of x equals g of f of x equals x, the functions are inverses. And we're going to practice this extensively in section 1.3. True, false. True or false, the function given here is an even function. Justify your answer. It is false. If I plug negative x in, I do not get the same function back out. Yes, this term is the same because I raise it to the 4th power. It turns positive. Negative raised to the 2nd power stays positive. This becomes negative x. They are not the same. You could also verify it by just plugging 1 in and then plugging -1 in and showing that there is no correlation. We did not get the same thing back out. True or false? Is this an odd function? This would be true. Make sure that we know that x to the -3rd power is 1 over x cubed. If I plug negative x in for x, a negative sign cubed is still negative. And I can put the negative on top instead of on the bottom. I get the same function back out, but opposite sign. Whenever you get the same function back out, but the opposite sign, it's an odd function. 59. What is the domain? Here's how I want you to be able to think about domain this quickly. When does this equal? It's an even root. Okay. So there's 2 things I need to be concerned about. Number 1, I cannot take an even root of a negative number. Number 2, I cannot divide by 0 because this is in the denominator. So what makes this argument equal 0? -3 and 3. There's 2 solutions to this quadratic, not 1, there's 2. And I just got to determine, do the numbers in between work or do the numbers on the outside work? Just plug a number in between. -3 and 3, like 0. Yeah, 0 works. 9 is greater than 0. That works. I can take the square root if I plug 0 in. The values that have to be eliminated are to the right and to the left. The domain only consists of the values from -3 to 3. Notice it's an open circle, so parentheses, not brackets. If this same square root was in the numerator instead, it would be bracketed. The only reason why -3 and 3 are eliminated is because those values make the denominator equal 0. That's how this becomes a domain. Notice this is interval notation. The inequality notation would be -3 less than x less than 3 because it's an and. It's the area in between. It's an and. 60. Which of the following gives the range? This is a tough problem. Here's why it's a tough problem. I like to sometimes look at this as all one function. You don't have to, but I got a common denominator. I said I'm going to multiply this 1 by x minus 1 over x minus 1. So I can take x minus 1 plus 1, showing that right here, all over the common denominator. The ones cancel, and I get this. Now the degree on top is the same as the degree on the bottom. So y equals 1 is the horizontal asymptote. So the range is not going to be all real numbers. That's why that's canceled. Okay? Range defies the y values, not the x. They're trying to get you to fall for the domain here. So I cancel those two out. It's going to be this. Well, what I know is that this function is not going to equal that horizontal asymptote. It's 1 that has to be eliminated from the range. This eliminates 1. Notice it's that notation I showed you before, where this is how you eliminate 1, the value of 1, using interval notation. If I were using inequality notation, I would just write y cannot be 1. Just like this, except it'd be a y. So this is tempting, but this says x can't equal 1. I got to know it's y can't equal 1 is the range. Okay? That's why A is the answer. 61. Which of the following gives you f of g of 2? That's what f circle g. This is not a multiplication, it's a composite. So 2 goes into the g function. I show that right here. 5 comes out. So now g of 2 gets replaced with 5. What is f of 5? 5 comes into the f function. 10 minus 1, 9 comes out. That's why D is the answer. Last multiple choice. The length of a rectangle is twice as long as the width. There it is right there. Write that equation down. Which of the following gives the area of the rectangle as a function of the width? You're going to do lots of this in chapter 5, where we know the area of a rectangle is length times width, except we want to write it as a function of one variable, not two variables. So I have to write it as a function of the width. Okay, I'll just replace L with 2W. If I replace L with 2W, 2W times W is 2W squared, C. But this is a very important skill in chapter 5. Okay, I'm going to end up stopping the recording here on this. Hopefully that went well. You can go back and look at this, and I will put it out when this is assigned. I'll put it out to you. Okay.